Welcome to lesson 1.2, the domain and range of a function. Goals. Today we set out to 1. Express one-dimensional spaces as inequalities and as intervals. 2. Determine the domain and range of a function analytically. 3. Determine the domain and range of a function graphically. And 4. Construct and evaluate simple piecewise functions. First, we will express spaces as inequalities. Imagine the number line containing all real numbers, the numbers contained between negative infinity and positive infinity. Here is our number line. In the middle of our number line, we'll place 0 as a frame of reference. We fill in our integers, moving up to 6 on the positive end and -4 on the negative end, and we allow the space to the left and right of those to be infinity and negative infinity. Suppose we wanted to visualize the space of all non-negative numbers. We certainly start at 0, and we have a dot right above 0. And then we'd include all values to the right of 0. We depict all of these values by drawing an arrow to the right. So now we're going to express this space in a succinct mathematical way. We'll start with inequalities. The lower bound of our space is 0. So we have an inequality saying 0 is less than or equal to x, which is less than infinity. And we include 0 in that space. So now we put a line under the inequality symbol to the left of x. And now we have 0 is less than or equal to x, which is less than infinity. The upper bound of this space is infinity, but we don't include, we don't include the number infinity because there actually isn't a numerical value to infinity. It also seems redundant to say x is less than infinity because of course it is. So our final inequality would be expressed as 0 is less than or equal to x. Now suppose we wanted to visualize the space of all numbers in between -2 and 3, and we will include -2 in this space. We'd certainly start at -2, so we put an open circle over -2. We'd want to include all the values up to 3, so we'll put an open circle at 3. And we draw a line segment between those 2 points, those 2 circles. The lower bound of our space is -2, and we include -2 in that space. So we'll go ahead and fill in the circle at -2. And so now we have the inequality -2 is less than or equal to x. And the upper bound of our space is 3. So now we have that x is less than 3. So our inequality at this juncture is -2 is less than or equal to x, which is less than 3. Since we don't include 3, because we never said we would, we're going to leave that circle at 3 open, and we're going to leave that inequality for 3 strict, meaning that we don't include 3. So our final inequality is -2 is less than or equal to x, which is less than 3. Suppose we wanted to visualize the space of all numbers less than 5. We're now going to do this with intervals. We'd certainly start at negative infinity, which seems like a silly place to start, but that is the leftmost point for which we would attain. And we would go all the way up to 5. So at 5, we're going to put an open circle there. And we have an arrow going to the left of 5 to signify our start at negative infinity. The lower bound of our space is negative infinity. So we have negative infinity and then a comma. And we don't include negative infinity in the space, so we put a parenthesis around the negative infinity on the left-hand side. The upper bound of our space is 5, so after the comma, we put a 5. And since we don't include 5, we also put a parenthesis around the right-hand side of 5. And so now we have our interval, which we write as parenthesis, negative infinity, comma, 5 parenthesis. Suppose we wanted to visualize the space of all numbers greater than or equal to 2, but excluding 4. We'd certainly start at 2. So at 2, we're going to have a closed circle because we are going to be including 2. And we're going to include all values up to infinity, but we're going to skip 4. So we're going to draw an open circle around 4, and we're going to draw our arrow around that open circle, basically. Here we have 2 separate spaces. Our lower bound is 2 and includes 2. And so we use a bracket. So we have bracket 2, comma. And our upper bound is 4, but it's not going to include 4. Because if we included 4, then we would be including 4 in our space. So we put a parenthesis around 4. So our lower bound space, or one of our spaces, is going to be bracket 2, comma 4, parenthesis. But we also have the space to the right of 4. Here our lower bound is 4, so we use a parenthesis around 4. And we go all the way up to infinity. And so we put a parenthesis around infinity because we certainly can't include infinity. But we have to put these two spaces together. So we use a union, which is U, to put these two spaces together. And so that's how we would write this space. Just for clarity, it would be bracket 2, comma 4, parenthesis, union, or U, parenthesis 4, comma, infinity, parenthesis. Now we're going to talk about the domain and range of a function. The purpose of those few exercises was to help us expressing single-dimensional spaces. This will help us as we express the domain and range of functions. The domain is defined to be the set of all possible input values to a function, and the range is defined to be the set of all output values of a function. So when we're trying to find the domain, our big question is, which numbers serve as legal inputs for our function? This leads to a more interesting question, which is, what aren't legal inputs? Why aren't they legal? Illegal inputs. We can't plug numbers into a function, f of x, if the following occurs. 1, if we divide by 0. We have an example function here. We'll call it f of x, and we'll say that function is 1 over x minus 3. Without too much thought, we see that if we plug 3 in for x into this function, we have that f of 3 is 1 over 3 minus 3. Well, that's 1 over 0, and that's a problem. 3 is the only illegal number in this case. So the domain is every real number except for 3. The next thing that's illegal, number 2, is a negative number under a radical of even index. So consider our new example function. We'll say it's f of x is the square root of 2 minus x. If I plug anything bigger than 2 in for x, so suppose I plug in 5, then I get the square root of 2 minus 5. That's the square root of negative 3. What we now have is any number bigger than 2 is illegal because I can't take the square root of negative 3 in the real numbers. So the domain is all numbers less than or equal to 2. We'll work on expressing those spaces more succinctly in a few minutes. So when we talk about range, the big question is, what numbers can I get as outputs for a function? So if we look at this example, we have a table that shows a relationship between circumference and height of a tree as it grows. In our we have a 2-row table present. We have a circumference row labeled C and a height row labeled H. In the circumference row, we have 1.7, 2.5, 5.5, 8.2, and 13.7. In the height row, we have 24.5, 31, 45.2, 54.6, 92.1. For our domain, the question we're asking is, how small or large can the circumference reasonably run based on the data given? And we see that 0 is less than C, which is less than or equal to 13.7. Certainly C could not be equal to 0 because that would be a little silly to consider a tree with a circumference of 0. That would not be a tree. That would just be kind of nothing. Our range, the way that we could also write our domain, by the way, in interval notation would be parenthesis 0, comma, 13.7 bracket. For range, what we should be asking is, how small or large can the height reasonably run based on the data that's provided? So we would say 0 is less than h, because again, a height of 0 is absurd, is less than or equal to, 0 is less than h, which is less than or equal to 92.1. If we were going to write that as an interval, it would be parenthesis 0, 92.1 bracket. Now what we're going to do is determine the domain of a function analytically. So here we have an example, and what we're going to do is determine the domain of the function given below. Our function is f of x, which is equal to the square root of 5x plus 2. We have a number line shown, and we have what's called the implied domain, which is all real numbers. We have a red line over our number line to signify that we are allowing for all things to be allowed for our domain for right now. And what we're going to do is restrict that based on values that we find to be illegal. For our procedure, the first thing we are going to do, we have number 1, remove divisions by 0 from the implied domain. Well, in our function, observe that we have no divisions, so we don't need to worry about that. There's no divisions by x or any input variable that would make us divide by 0, so we don't need to worry about that. Next, in procedure step 2, we remove negatives under even indexed radicals from the implied domain. Okay, well, in order to do that, I need to find where those are. So I have the inequality 5x plus 2 is less than 0 because I want to find out where these values are negative. I'm going to subtract 2 from both sides of this inequality, so I get 5x is less than negative 2. And now I divide both sides of this inequality by 5, so I get x is less than negative 2/5. So what that means is I now have an open circle at negative 2/5, which is about negative 0.4. And if I draw an arrow to the right, I'm creating a separate space underneath my implied domain. These are values which are illegal. So now what I'm going to do is remove those values, which is going to leave me with a closed circle at negative 2/5. And I'm going to keep all of the values to the right of that. So I've removed all of the illegal things. So what I'm left with are the legal things. And now I'm going to express my final interval or inequality. This is step 3 of my procedure. So if I write this as an interval, I'm including negative 0.4 in the space, and I'm going all the way to the right. So I would use the interval bracket, negative 0.4, comma, infinity parenthesis. As an inequality, I would say x is greater than or equal to negative 0.4. All right, now we're going to determine the domain of the function given below. This is our second example. Our function is f of x, which is the square root. It's the square root of 2 minus 3x divided by 2x squared minus 5x minus 3. Again, my procedure, the first thing I'm going to do is remove divisions by 0 from the implied domain. This is the first step of the procedure. So first, I'm going to set the equation 2x squared minus 5x minus 3 equal to 0, and I'm going to solve for x. You can use quadratic formula or factoring for this. I'm going to leave that detail to you, the viewer. We get that x is equal to negative 1/2 and x is equal to 3. So at these particular values, I would be dividing by 0 if I plugged them into the function. So what I'm going to do now is go into my implied domain, which was my number line that I drew, which is my number line directly over the number line that's given. And I'm going to draw an open circle at negative 0.5. That's going to help me remove that point. And then at 3, I'm going to draw an open circle. That's going to help me remove that point. The second step of my procedure, step 2, is to remove negatives under the even indexed radical from the implied domain. So now I'm going to set up the inequality 2 minus 3x is less than 0, and I want to solve this for x so that I can find out where the illegal values would be in my numerator. So I'm going to subtract 2 from both sides. I get negative 3x is less than negative 2. So now I'm going to divide both sides of this inequality by negative 3. Something that's important to remember is when I multiply or divide both sides of an inequality by a negative number, that reverses the orientation of the inequality. So where it was negative 3x is less than negative 2 before, after I do my division, I have x is greater than 2/3. So now my final inequality is x is greater than 2/3, which means at 2/3, which is about 0.66, I'm going to draw an open circle. And I'm going to have an arrow going to the right. This signifies all of my illegal values. So that's going to leave me in the domain with a closed circle at 2/3, and everything to the right of that is going to be erased, including the open circle we have at 3. And so now we have this space going from negative infinity, stopping at -1/2, and then at an open circle at -1/2, and then going from -1/2 up to 2/3. Now we're going, in this third step of our procedure, we're going to express our final interval / inequality. Our interval would be parenthesis, -infinity, -1/2 parenthesis, union, parenthesis, -1/2 to 2/3 bracket. Our inequality would be x is less than or equal to 2/3 and x does not equal -1/2. This is a totally appropriate way to write an inequality. You can absolutely use pieces of spoken language for that when appropriate. Now we're going to talk about the domain and range of a function's graph. Again, as a reminder, our domain and range definition, we define the domain to be the set of all possible input values to a function. We define the range to be the set of all possible output values of a function. Below, I've got a picture of a blank X and Y graph, XY grid. I drew a circle around the X-axis. That is my input axis. The big question here is which values from left to right are used on the X-axis in this function. That's how I address the question of domain. Now I've drawn a circle around the output axis. The big question here is which values from bottom to top are used on the Y-axis in the function. Now I'm going to state the domain and range of a function's graph. I have a graph pictured here, and it's on an XY grid. The X values go from -1 to about 4. The Y values go from about -1 to 6. We have a quadratic parabola, but we only have a very small snapshot of it. We don't have the entire parabola. The parabola starts, it's a parabola opening down. And at the coordinates 0, 1 is where we have a closed circle where it begins. And at the coordinate points 3, 4 is where there's an open circle at the end of it. The vertex of this quadratic parabola is at the coordinate pair 2, 5. Now, for the domain of this graph, what I'm going to do is look from the left to the right. I'm looking for the leftmost point and which X value it occupies. If I look on this graph, I see all the way to the left, while it may be touching 1 on the Y-axis, its associated X value is 0. And it's going to include 0 because that is a closed circle. It goes all the way to the right to the X value of 3, and that is an open circle. So my domain is going to be bracket 0, 3. My range, I want you to observe that the lowest Y value that this function takes on is 1, and it does take that on with a closed circle. So 1 is going to be the lower bound of my range, and it goes all the way up to 5. When it goes up to 5, it does actually touch the Y value of 5. If I drew a horizontal line of Y equals 5, I would see that the vertex is on this line. So I'm going to have the range of 1, 5, both with brackets shown here. Now I've got the graph of a cubic polynomial. The domain of this cubic polynomial, we have arrows on both sides of the graph. So that means that it's going to go all the way to the left and all the way to the right on the x-axis. That means that its domain is going to be -infinity to +infinity, and those are both going to have parentheses because I obviously cannot include the infinities as points on a graph. The range, because of those arrows, they're obviously going all the way down and they're going all the way up. So our range is going to go from -infinity to +infinity. Next, I've got a reciprocal function. This reciprocal function has a horizontal asymptote at y equals 2 and a vertical asymptote at x equals 3. The domain of this function is going to go all the way to the left, in particular from -infinity up to 3, but observe that I cannot allow 3 to be in the domain of the function because of the vertical asymptote. Next, after 3, my x values pick right back up and move all the way to the right. So my domain is going to be parenthesis negative infinity to 3, parenthesis, and then union 3 to infinity. This same observation takes place on the y-axis, where since I've got an arrow going all the way down, I'm starting at negative infinity. I'm going all the way up to the y value of 2. I am not including 2. So that's why I use the first range space of negative infinity to 2, parentheses around both of them. But I'm going to union that with 2 infinity because my y values pick right back up at 2 and then go all the way up to infinity. These are going to be tricky at first, and we are going to be drawing out much better language surrounding asymptotes when we get into section 3.7 much later on in the semester. Next, we're going to talk about piecewise functions. A piecewise function is a function in which the formula used depends on the domain the input lies in. We notate this idea like this. F of x is equal to, and then we have a curly brace creating 3 different lines. The curly brace extends all the way up to formula 1, if domain to use formula 1. In the middle, we have formula 2, if domain to use formula 2. And then formula 3, if domain to use formula 3. How do these things work? So suppose we have, this is an example of a piecewise function. A museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for $10 or more people, or for 10 or more people in the group. Set up a function relating the number of people n to the cost c. So we have this function c of n. For groups of size between 0 and 10, we're saying if 0 is less than n is less than 10, to the left of that, we're going to write the formula, which would be multiplying the size of the group by 5 to get the total cost. Therefore, that would be 5n, because we defined our variable to be n. So in our curly brace, in the top line, we have 5n if 0 is less than n is less than 10. For groups of size 10 or over, our domain for the second line would be if n is greater than or equal to 10, and our formula would be a flat fee of $50, so it would just be 50 to the left of that. So our second line would read 50 if n is greater than or equal to 10. And so this formula together forms the piecewise function of c of n. We will do another example for piecewise functions. A cell phone company uses the function below to determine the cost c in dollars for g gigabytes of data transfer. We have the function c of g is equal to the piecewise function 25 if 0 is less than g is less than 2. And then the second line reads 25 plus 10 times g minus 2. G minus 2 is in parentheses. If g is greater than 2. Find the cost of using 1.5 gigabytes of data and the cost of using 4 gigabytes of data. So for the first part of this problem, we're computing c of 1.5. Observe that the value 1.5 exists in the domain of 0 to g to 2. So we would use the formula 1. In particular, the constant 25. The user will pay $25 for a 1.5 gigabyte transfer of data. Now for C of 4, we consider first where 4 lives. 4 lives in the domain g is greater than or equal to 2, so we're going to use formula 2. Instead of distributing the 10, I'm simply going to plug the 4 in, so I get 25 plus 10 times 4 minus 2. So 4 minus 2 is 2, so I get 25 plus 10 times 2. The user will pay $45 for a 4 gigabyte transfer of data. Now we're going to graph piecewise functions. I've got a picture of a grid, an XY grid. The X values go from negative 10 to 10, and the Y values go from negative 10 to 10. And I am asking you to sketch a graph of the function given. We have a piecewise function. Formula 1 is -4, and that domain is from -6 is less than or equal to x is less than 0. Formula 2 is x squared. With its domain 0 is less than or equal to x, which is less than or equal to 3. And I've got x with the formula 3, I'm sorry, is x with the domain of 3 is less than x. For our procedure, step 1 is to graph all of the functions. So we take all of these functions and we put them all on the grid together. It's going to look like a big old mess. But here we have a constant function at -4, which is a horizontal line at y = 4. We have a quadratic parabola passing through the point of origin because we didn't do any transformations. And we have the identity function, which is x, and that is also on top of this graph. And so they're all plopped on there together. It's kind of a mess. But now what we need to do is the second part of our procedure, which is to delete the portions of each function outside of its given domain. So we're going to start with -4, formula 1. Its domain is supposed to be from -6 to 0. So I'm going to draw a horizontal line at -6, and I'm sorry, a vertical line at -6 and a vertical line at 0. And I'm going to erase the constant function on either side of those lines. So I'm going to erase the part of the horizontal line to the left of the vertical line, x = -6, and I'm going to erase the horizontal line to the right of the line x = 0. And so now I've got a line segment of the horizontal line at y = -4, and that's ranging from -6 to 0. We'll get to the endpoints for the third part of our procedure. Now for formula 2, I draw a vertical line at x = 0 and at x = 3, and I'm going to erase the part of this quadratic parabola to the left of x = 0 and to the right of the line x = 3. And so now I have a segment of a quadratic parabola, and I'm not going to worry about the endpoints yet. I repeat this procedure for the identity function. I draw a vertical line at x = 3, and I erase the portion of the line to the left of x = 3. And now I've got a ray starting at the coordinate pair 3, 3, and it's going all the way to the right. That has an arrow on the end of it on its right-hand side. Now I need to do the endpoints. So I'm going to add either open or closed endpoints based on the inclusion or exclusion of each portion's endpoints. So now I'm going to look at formula 1, since the horizontal line goes from -6 to 0. -6 is included, 0 is not. At -6, I'm going to put a closed circle, but at x = 0 on the horizontal line, I'm going to put an open circle. Now I jump up to the parabola. And at 0, at x = 0 on the parabola, I'm going to have a closed circle. And at x = 3 on the quadratic parabola, I'm going to have a closed circle as well. So I put closed circles on those endpoints. And since on formula 3, the identity function, since 3 is a strict inequality there, I'm going to put an open circle on that. And this is going to pass the vertical line test. This is a piecewise function. And now we're going to move on to another example where we're going to be doing this same procedure, but I went ahead and already drew the lines on there for you. And so we've got a sketched graph of a piecewise function where formula 1 is the absolute value of x, where 1 is less than x, and the cubic root of x, where -1 is greater than or equal to x. This is really just a game of recognition of toolkit functions and their application in piecewise. So what we have is the graph, the cubic root of x function to the left of -1 on the x-axis. At x = -1 on the cubic root function, we have a closed circle because I do include that in my domain for formula 2. And then we jump over to formula 1, which is our absolute value function, which has an open circle at x = 1. And it is an absolute value function with a vertex at the point of origin, 0, 0. And that extends all the way to the right. Observe that at both ends of this function, the cubic root function, there is an arrow extending to the left, and on the absolute value function, there's an arrow extending to the right. Now suppose we went the other direction. So now we're going to go, instead of graphing a piecewise function, I'm going to give you the graph of a piecewise function, and you need to write a formula for the piecewise function graph. So we have a horizontal line starting at negative infinity and stopping on the y-axis at 3. So we have a horizontal line, y equals 3. And it goes all the way to the left, and it stops on the y-axis with a closed circle. Then we have a parabola starting at the point of origin. Its vertex is at the point of origin with an open circle, and that parabola is extending all the way to the right. So we need to come up with a piecewise function that models this picture. We'll call this function g of x. So I broke this function up into 2 formulas. Formula 1 would be the y equals 3. And I just wrote 3, where x is less than or equal to 0. And then formula 2 would be x squared, where x is greater than 0. These take a little bit of practice, and they require a functional understanding of your toolkit functions. So be kind to yourself as you're learning this.